Here's the tutorial on the Chatelier's principal Fakie. So we have a balanced reaction. I'm not asking you to balance them for this quiz. Let's note a few things though. A system that is in equilibrium, that should be a double arrow, showing that it's in equilibrium, always shift away from the stronger side and toward the weaker side, whichever way that is. Also, if the volume of the system goes up, that's like expanding the balloon, and that means that things are less crowded, which means the pressure is going down. And then the opposite also, if the volume is going down, the balloon is getting squeezed, and the crowdedness or the pressure is going up. If the delta H value is a negative number, then it is exothermic. This reaction is exothermic. The heat or energy is coming out. It is a product. The heat lives on the right side of the arrows. By the way, that means kilo or thousand, and that means joule, and that's Joule. There was a Dr. Joule, and so that's named after a person. It is not a reference to diamonds and rubies and so forth. So let's do some examples here. If we decrease the CH4, we put something in the box, in the vessel, that soaks up the CH4, so to speak, then the amount of this goes down. We're decreasing it. That weakens the left side. It means the left side has less of what it needs to do its job, because it needs one of these and two of those. So this is the weak side, and we said the system always shifts toward the weak side, so it's going to shift toward the left. It's going to make more of the left for a moment than it is the right. So it's shifting left. So to break that down even farther, what I mean is in equilibrium, when it's at equilibrium, we do not mean that it has equal numbers of the chemicals. We mean that the rates are equal. So it's going one left, one right, one left, one right, equally. And so when I say that it shifts left, it's something like we're getting two lefts made for every one right made, and two and one and two and one, which means that we're making more of this than we're destroying, and we're destroying more of these on the right side than we're making. And so we call that shifting left because we're getting more of the left side made than the right side. So what is the effect of on the concentration of the CO2? The CO2 is on the right side, and the H2O is also. And we said we're destroying the right side faster than we're making it. We're using it up to make the left side faster than it's getting remade by the system going to the right. Because remember, we said it's something like make two lefts, make one right. Make two lefts, make one right. So the amount of these, all three, including the heat really, are going down, and the lefts are going up. So if this asked what's happening to the O2, the answer would be that it is going up, it is increasing in concentration. On 2, though, let's increase the temperature, and we can sort of regard the heat as a reactant, or a chemical, I should say. So if I increase the temperature, I'm giving the right side something it needs. It needs one of these and two of those and some heat. So if I give it heat, I'm giving it more of what it needs. And so this is the strong side, and it always goes toward the weaker side or away from the strong side. So this also shifts left. And that means these two go up and these two go down. So that's an up and a down. If we decrease the pressure, now this gets a little bit more logicalness. We need to count the gas molecules. The liquids and solids don't matter for discussing the pressure and volume changes. So let's count the gas molecules. 1 and 2 gas molecules means this is a side with 3 gas molecules. Notice this is a liquid, and that is easy to get fooled with, and it's fooled me. So this is a 1 gas molecule, that's parentheses G, 1 gas molecule side. So if we decrease the pressure, we said that's the same as the volume going up. So the balloon is getting unsqueezed. So the more simplistic way to find the answer is which side of this reaction is looking to fill more space compared to the other one. The 3 gas molecule side is looking to fill space more than the 1 gas molecule side is. Now then I get kids saying, so this is the strong side? No, this is the side that will do a better job of filling the space, and that's the one we will get more of. When I'm describing it in these terms for pressure and volume, I'm not doing a strong, weak. I'm saying which one would you get more of? Which one fills the space better? The extra space, because we're getting extra space because the volume is going up. And the answer is the side with more gas molecules. It will fill the extra space better. So we will get more of the side with more gas molecules. And this time that is the left side. So this will shift left. So it's shifting left, which means we're using up all the stuff on the right. We're making more of the stuff on the left. So something on the left goes up. Something on the right, I should say, goes down, and something on the left goes up. Now, here's a description for the people who want to go one step deeper into this. If I decrease the pressure, I am affecting the gas parts of these reactions. But let's talk about the opposite for a moment. If I make the volume go smaller, I am squeezing the balloon, so to speak, and I'm cramming everything together. So let's even pretend that this is a 2 gas molecule side for just a moment. What's harder to do, to get 3 gas molecules to meet in one spot to react, or to get 2? Well, 3 is harder to get to meet in one spot than 2. So when I cram this all together, I'm helping the side more that has the harder job to do, and that is the side with more gas molecules needing to meet. So just for some dumb numbers, let's pretend I'm helping this side by 20% when I squeeze this down, but I'm helping this side by 35%. It's probably even more than that. So I'm helping this side more. If I'm helping this side do its job better, more than I am that side, then this is the strong side, and it will shift to the right. And some of you just shouted, you said it shifts to the left, because I am describing the opposite. I said if we squeeze the balloon. If we squeeze the balloon and the volume goes down, then I'm helping this side more, and it will shift to the right, because I'm helping this side more than I'm helping that side. Now this problem here did say the volume goes up. So let's run this all backward. And remember, a real key phrase to this whole unit is if you do the opposite, you get the opposite. So if I do the opposite and I unsqueeze the balloon, then I unhelp the left side more than I'm unhelping the right side. Or I hurt the left side more than I'm hurting the right side, which makes this the weak side, which means the system will flow toward the weaker side. It will flow to the left, and we get the same answer. Now, that is really the more science-y explanation. And if you're going to end up in a science-type chemistry, college class, then I would try to understand that explanation. And you can email me more questions if you need to. If it's flowing left, then everything on the right is going down, everything on the left is going up, so that is a down-up. Here we have delta H as a positive value. Again, that's kilojoules, so it's the opposite. This is an endothermic. Heat is going into the reaction more than it's coming out, so heat is a reactant, so to speak. It goes on the left. Now, I'm not asking you if it's endothermic or exothermic, but for all you people who are going to end up in a college class, those are fine science words you should learn. Endo means inside, exo means exit. Like crabs have an exoskeleton, but you have an endoskeleton because your skeleton is on the inside of you. So endo means interior or in. So the heat is going into the reaction. There's more heat going in than coming out. So overall, we're going to apply the net heat effect on the left. So 4 says decrease in H2O. H2O is on the left. If I decrease that, that makes that the weak side. Everything will go left. which means we'll use up these and make more of those. So NO goes up and NH3 goes down. If I decrease the temperature, I am hurting the side with the heat on it, which means I'm hurting the left side. So everything goes left, which means all of these go down and all of these go up. So that goes down and that goes down also. Increase in pressure. How do you make this more crowded, make the pressure go up? You squeeze the balloon, the volume goes down, and now we need a count of the gas molecules, and this is skip that one. That's a liquid. So 4 gas molecule side versus 9 gas molecule side. So if I'm squeezing the balloon, as I described up here, I'm helping the side more that has more gas molecules. So I'm helping the right side more, and everything will go left. Or, if you want a simpler explanation, which one will fit into the smaller space, the new smaller space, better, and that's the one that you'll get more of. And 4 gas molecules fits into the smaller space better than 9 gas molecules does, so we will get more of the left, and we get the same answer. It shifts left. And everything on the, it shifts left. No, it shifts left. There we go. And we will get less of the stuff on the right and more of the stuff on the left. So the O2 goes down and the H2O goes up. Delta H is a negative number, so the heat goes on the right. How can we make this shift to the right? We had to make this to be the weak side and that be the strong side. So I'm going to increase everything over here. And I'm going to decrease everything over here. And then I have the question of volume and pressure. So I need to count the gas molecules. And 2 and 3 is 5, and that makes 7 gas molecules and 2 gas molecules. So since this has more gas molecules, what I want to do to make this be the strong side and that the weaker side is I want to squeeze these down so that I'm helping this side more than that side, because it's a tougher job to get 7 gas molecules to meet in one spot to react than it is with 2. And if I squeeze it down, I decrease the volume, which is increasing the pressure, I will make this the strong side and that the weak side. Or we could just say, which one favors less gas molecules? A smaller space is what is going to be favored, and it will go to the right. A smaller space decrease the volume. Or maybe you think of it this way, and this is the kind of the way I think about it. I think of the opposite. If I expand this balloon, which one fits into the bigger space better? Which one wants a bigger space? And the answer is the left side. So if I open the balloon more, if I expand it, I'm going to send things to the left, but I want to send them to the right. So I'm going to squeeze the balloon. That's a decrease in volume and an increase in pressure. Now, B is just sort of a lesson in, if you want to do the opposite, do the opposite. If you want it to go left, just turn everything around. On 8, I just made up my own theoretical, it should be an equilibrium. Oh, whoopsie. It should be a double arrow. Equilibrium arrows there. I made up my own reaction. And I got a 4 gas side and a 2 gas side. And so I want it to go left. That means I increase everything over here and decrease everything over here. And if I want it to slide left, I want the volume to go up to accommodate more gas molecules, the one side with more gas molecules, which means the pressure goes down. And if I want to get the opposite, I do all the opposite of what I just said over here. So I want this to go to the right. Increasing the pressure will get me more of the side with fewer gas molecules. So that's this side. So that's a yes. I circle that. That was true. This is basically the same thing as that. If I squeeze the balloon, I make the volume decrease. It's getting smaller because I'm squeezing it. That will increase the pressure. So this is basically the same thing, A and B. So yes, that will make it go to the right, toward the side with fewer gas molecules. Increasing D would empower the right side and not the left, so that would make that be the strong side, which would send everything to the left, so that is wrong. Decreasing D, well, if you do the opposite, you get the opposite. So if I do the opposite, I will get it going to the right, so that is true. That would work. Count the gas molecules. The amount of SO3 will increase. Well, that would be if this slides to the right. If it's going to the right faster than it's going to the left, then I will get an increase in SO3. So again, I want this all to go to the right. An increase in temperature, though, would empower the right side. Now, also, some kids said, then yells, but that's a positive number. And you said the positive numbers go on the left, but that is when it is delta H. Delta H equals positive, goes on the left side. Delta H is negative, goes on the right side. Whoops, delta H is negative, goes on the right side. This does not say delta H, and I know that is kind of a picky point, but these are often written like this. And, this is a class with a lot of details in it. So this is the heat right here. It is already placed on the right side for me. So an increase in temperature would empower the right side and make it go left, so that does not get me what I want. An increase in pressure would favor the side with fewer gas molecules, which is the right side, so that is true. An increase in concentration of SO2 would make the left side the strong side, so that will go right, so that is true. An increase in O2 is also empowering the left side, so it will go right, so that is true. If I increase the H2, that empowers the left side, and everything will go to the right. Note to self. So what happens? The equilibrium shifts left. That can't be correct, so these are out. It shifts to the right. It's got to be C or D or both or something. And the concentration of N2 increases. N2 is on the left, and if I'm shifting this to the right, then everything on the left is getting used up more than it's getting made, so the concentration of N2 should decrease. So C is wrong and D is correct. On 12, I'm going to count my gas molecules because I bet that comes up. So that's a 4 gas and a 5 gas molecule side. The delta H is negative value, so the heat goes on the right side. Decreasing the volume squeezes it down and favors the side with fewer gas molecules, and that means it goes left. And the water is on the left, which means I will get more of it because we're getting more of the left side and less of the right side as this slides or shifts to the left. Adding oxygen empowers the right side, meaning it goes left. The concentration of water, again, will go up if you shift it left. So we get the same thing there for water. Removing oxygen. If you do the opposite, you get the opposite. So if I remove oxygen, it will slide to the right, and HCl is on the right, so I will get more of it that I'm destroying for a moment there. Increase the volume of the container would mean that I favor the side that has more gas molecules, so I will get more of the right side, and this will slide to the left. The chlorine is on the left side, though, so it is getting destroyed faster than it's getting made. Decrease the volume. Well, if you do the opposite, you get the opposite. So this is going to go left, and the oxygen is on the right, which means it's getting chewed up faster than it's getting created. Lowering the temperature. The heat is on the right, which means this is weakening the right side, which means everything goes to the right. And the water is on the left, which means we're using it up faster than we're making it. Raising the temperature. If you do the opposite, you get the opposite. So raising the temperature means the right side is the strong side, which means everything goes left, and you get more of the stuff on the left. Adding a noble gas does nothing. This is the chemical family, the vertical column on the periodic table under helium on the full right side. It just gets in the way of everything pretty much equally, and you get no effect. So that is the trick question, except I'm telling you the trick question. And so if you have no shift, then the concentration of oxygen doesn't get affected. So this is just, forget it, nothing. The answer is none. Adding a catalyst does nothing. And so the effect on the chlorine, or whatever it would be nothing. And to go one step deeper, a catalyst makes a reaction run faster, and we usually mean to the right. Whichever way is depicted to the right. If it's a catalyst for the reaction, we mean it makes it run faster to the right. Now, some kid yells, you just said it goes faster to the right. Yes, but what happens is because we haven't changed the amounts of anything, including the heat, right? It runs faster to the right, but then the right side gets stronger and immediately starts running faster to the left. And by the time you get done, you're right back where you started. And everything is running faster, and you don't have any more or less of what you ended up with, so the amount of chlorine is unaffected. Raising the temperature, we said, empowers the right side, so it goes left, and the amount of chlorine on the right side goes up faster than it's being destroyed. Removing HCl decreases the power of the right side. It weakens the right side, which means everything goes goes right. And the heat is on the right, so we're getting more heat than we're using. Taking away O2 weakens the right side, so everything goes to the right. And the H2O is on the left, which means we're using it up faster than we're making it.